So far, we have looked at some general matrices. General matrices have n rows and m columns, where n and m are any natural numbers. Then we have looked at some special matrices, like square matrices, which have the same number of rows as columns. There are two other matrix dimensions of great importance in matrix algebra. The first one will be called row vectors. And the row vector is simply a matrix with a single row. That means that the first dimension index, the one that tells us how many rows the matrix has, must be 1 for a matrix to be a row vector. The second dimension index, the number of columns, may be any number. We also have something which will be called column vectors, and a column vector is then simply a matrix with a single column. And that, of course, means that the second dimension index must be 1 for a matrix to be a column vector. So here's an example of a row vector. It has only one row, as we can see. It has 3 columns, and that's why it's a 1 by 3 row vector, or a 1 by 3 matrix, if you like. Here is an example of a column vector. It has only a single column. It has 2 rows, so it's a 2 by 1 column vector, or a 2 by 1 matrix. So row vectors and column vectors are always special kinds of matrices, while a matrix may be a row or a column vector. Remember that for a general matrix, an n by m matrix, we use the symbol small a and 2 subscript to denote the individual elements in the matrix. The first subscript referred to the row, while the second subscript referred to the column. For a row vector and a column vector, there is no need for 2 subscripts, and the standard notation is to use a single subscript. And so we will use a single subscript to denote the elements of a column vector or a row vector. For example, for the 1 by 3 row vector v minus 1, 0, 2, we have v1 minus 1, v2 0, and v3 equal to 2. It wouldn't be wrong to use the standard matrix notation and name the first element, the minus 1, to name that v1, 1, and the second v1, 2, and the third one v1, 3. That's okay, it's just a little bit unnecessary because the first index we know must be 1 as it has only one row. For this second example, when v is a 2 by 1 column vector, v1 is minus 1 and v2 is 1. Using standard matrix notation, we would say v1, 1 is minus 1 and v2, 1 is 1. Now, if we go back and consider a general matrix, an arbitrary matrix, and we call this matrix A, so it's an arbitrary n by m matrix. Here is an example of a matrix. It's 3 by 3. We know how to refer to individual elements. For example, this one here, the 4, that is called A, 2, 3, as it's on the second row and the third column. Turns out that quite often we need to refer to entire columns and entire rows in a matrix. So there is then a question of how to refer to, for example, this entire first column, and how to refer to this entire third row, for example. Unfortunately, there is no standard notation in the literature for referring to entire rows and columns, so I will use the following notation. Let's consider, for example, the third row. This row has elements A31, A32, and A33. That is, A with the first subscript 3 and the second subscript loops over all possible values. This is why I will refer to the third row as A3, comma, and then a colon, like this. So 3 means that we're dealing with the third row, and the colon means that we should basically use all possible values for the second index, 1 through 3. So that will be the notation for the third row. In precisely the same way, a 2 comma colon will denote the second row, and so on. If we consider the first column, this guy consists of the elements A11, A21, and A31. And here we see that the first index loops over all possible values while the second index is fixed at 1. So I will use the notation A colon comma 1 to denote the first column. Similarly, A colon comma 2 is the second column, and A colon comma 3 will be the third. So to review this, A I comma colon will denote the entire row I. That makes sense because the first index is the row index and it says that it should be row I. The second index is the column index, and the colon basically means all of them. That means that A I comma colon must be a row vector. It has a single row, namely row I of A. It will have the same number of columns as A because I pick out all the columns, and it means that A I comma colon must be a 1 by m row vector. Similarly, A colon comma j will denote the jth column of A. Again, notation, the first index is a colon, means all of them, so all the rows. The second index means the column index, so particularly column J. Since I'm pulling out all the rows for a particular column of A, that will result in an n by 1 column vector. So here's another example. A is a 2 by 3 matrix consisting of these elements. A1 comma colon, first row, all of the columns will then be -1, 2, 2, and A colon comma 1 will be the first column, -1 and 0.